So in a sense, now that is our Schrödinger's equation. Pardon, sorry. That is the analog of Newton's laws, Newton's second law. So Newton's second law just gave us a relation between acceleration and the force. Acceleration is nothing but how the position of an object changes as a function of time. And this equation just tells us how the wave function changes as a function of time. Now, in many of the questions that were asked during the break, you see, if you look at this equation, there is no probability over there. This equation is as deterministic as Newton's second law. What Newton's second law tells is that if you know the position and the momentum of your particles at this time and the interactions among them, then you can predict what they will do in the future, and you can also calculate what they did also in the past. What this equation tells me that if you know the wave function at a given time, this tells me that I can definitely predict the wave function in the future and also the wave function in the past. There's no probability over here. The probability enters into the game when you ask questions like, okay, what happens, what will be the outcome if you measure the position of the particle given the wave function? That is something that is still an open question. We don't have a definite interpretation of it. And that is a problem with the measurement. So you are measuring the position. What does it mean to measure the position of an object? But we will stick with the Copenhagen interpretation, where we have all this. We will be discussing about the probabilities. Now let's look at a simple problem. Well, before solving a simple problem, let's write a different problem, a different version of this equation. Now, when we were trying to motivate this equation, we started with a free particle and with a fixed momentum and a fixed energy. Well, a fixed momentum basically means that the particle is everywhere. The uncertainty in its position is infinite. As one of your friends had proposed, what happens if we put them in a wall? But putting them in a wall, basically, between two walls, is basically just putting a potential energy over there. So in that case, it won't have a definite momentum. It will have some uncertainty in momentum given by the v of x. But even your friend didn't propose what happens if we put some walls in time. So let's just localize it in time. Well, that's not something that we make sense of. So we can still ask the question, what if the particle has a definite energy? There's still a potential, but it has a fixed energy. So what we will do is we will look for a solution of this equation of this form. Times, okay, let me put the arguments also. This is psi of xt. Let me multiply with this phi of x. Does our Schrödinger equation have a solution of this form? Yes. The derivative? We will come to there. We will basically have two different cases. One where the walls are infinitely high. Then the derivatives exist, but they are not continuous. And secondly, the walls will not be infinitely high, but of a finite height. Then we will have a new phenomenon. But we will discuss it later on. Well, let's look at this. What happens if we know that we have a particle, we put it in a potential? No matter, you can just imagine various potentials. You can put a harmonic potential or walls at the end, etc. but what are the possible energy values? You see, we had already discussed the possible energy values of the hydrogen atom, possible energy values of the particle in a box. So eventually, I would like to apply my Schrödinger's equation to these problems and see if I can actually derive the same results as before, or will there be any other modifications on my previous results. But first, let's discuss what my equation will look like for wave functions corresponding to particles having a definite energy. We create a particle having a fixed energy. Then how will it change in, okay, then it will not change in time. Anyway, so let's see. Let me take the derivative of this thing. Well, the time derivative is only over here. So it gives me minus I e over h bar times e to the power minus I over h bar t times phi of x. If I take the derivative of psi with respect to x, this is e to the power minus I over h bar e of t, the derivative of phi with respect to x. Well, I just converted the partial derivative to total derivative here because there is no other argument there. Now, if I put them all up in the above equation, what I get will be I h bar. The derivative with respect to t is minus I over h bar e to the power minus I over h bar e of t of phi of x, which is equal to minus h bar squared over 2m e to the power minus I over h bar, well, the same exponent, the second derivative of this phi, plus v of x, the same exponent, times phi. Well, the exponentials, they cancel. If you have studied in 209 or 210 separation of variables, what I'm actually doing is just separation of variables. I'm just separating the time parameter from the position parameters. Now, h bars cancel. I times minus I just gives me 1. So I end up having this equation. This is what is called time-independent Schrödinger's equation. Now, why are we looking for such a solution? Because quite often, when we create our systems, we fix the energy. Energy is being conserved, it cannot change. So what I'm looking now here is what are the possible energy values. Also, eventually, we would like to look at certain phenomena that we observe in nature, like the spectrum. Well, we had already discussed the spectrum, the light spectrum arises because of transitions between energy levels. So if an electron has a definite energy, definite high energy, then when it makes a transition to a lower energy state, from a high energy state, it emits a photon. And the energy of the photon is the difference in these energy levels. So I need to determine the energy levels. What are the possible energy levels here? Because if you look at this equation, this is essentially what's called an eigenvalue equation. You see, if I define, let me call this H, I will put a hat on the top. H operator, this is minus h bar squared over 2m, the second derivative, plus v of x. Time-independent Schrödinger equation is this one. No, sorry. This is my time-independent equation. I have a wave function. I change this wave function by acting on it with a so-called an operator. What this operator does is it tells me to take the second derivative of this wave function, multiply it with this constant, and then add to it, take the wave function, multiply it with v of x. When I make these operations on this wave function, what I should obtain is exactly the same wave function with a coefficient in front. This is an eigenvalue equation. And E is the eigenvalue. And psi is called the corresponding eigenfunction. And quite often, you write E here. Well, because if you change E, you get a different function. To show that this eigenfunction corresponds to a given value of E, quite often you put some symbol index to explicitly specify. Now let's try to apply this to particle in a box. Well, the problem is, what is V of x for the particle in a box? Well, if we are inside the box, there is no force. So that's the definition of the box. So inside the box, the potential should be constant. And we can easily fix that constant to be 0. And outside the box, well, I will just assume that it is infinite. This will be the simplest solution. Later on, we will also study the case, what happens if it is not infinite? Well, let's look at our equation. E of psi, this should be equal to minus h bar squared over 2m d squared psi by dx squared plus, let's say, v of x psi of x. Now, why did I ask my wave function to be differentiable? Well, if it is not differentiable, this term, this expression over here doesn't make any sense. If I have, let's say, the existence of this term, you see, if you have a function that is discontinuous, you can either say, okay, its derivative doesn't exist. But for physicists, it exists, but it is infinite. You see, how do you define the derivative? Just a change in the value of the function divided by delta x. If delta x goes to 0, if there's a discontinuity, the change in the function does not go to 0. So you have a finite number divided by 0, which is infinite. And let's look at over here. You see, E is finite. So this should be finite everywhere. Of course, assuming that this is also finite. We will see. But mathematically speaking, if the derivative, if you have a function that is not continuous, then that term will be infinite. And you cannot have a finite energy solution with a finite potential. Some of them is eliminated if the potential is infinite. You see, in this case, we will see that the derivative is not continuous. Well, that's not really a problem, because the potential itself is also not finite. So let's see, what can be my wave function if x is less than 0 or x is larger than L? Outside the box, what does my equation tell me about my wave function? Yeah, you see, V is infinite, but energy is finite. So this term has to be finite or 0. But the only way that this term can be finite is if psi is 0. Otherwise, it won't be finite. So psi x is 0 if we are outside the box. So it kind of tells me that the probability of observing my particle outside the box is 0. Well, that is basically what is being inside the box means. You are inside the box, you cannot be outside. Okay, so what about let's solve this problem and then ask again. So for x between 0 and L, the equation I have is this one. E of psi of x is equal to minus h bar squared over 2m, the second derivative of psi of x with respect to x squared. I'm now inside the box. I know that outside the box, wave function is 0. Now I'm looking inside the box. Well, let's just let me define E as, this is the definition, h bar squared k squared over 2m. Why do I define it like this? Well, because I will cancel the h bar squared over 2m. So this tells me that k squared psi is equal to psi second derivative minus. Or the second derivative of psi is plus k squared psi is equal to 0. This is my equation. Now I said I want my wave function to be continuous. I know that outside the well my wave function is 0. So it should be continuous at x is equal to 0. But that tells me that psi at x is equal to 0 should be 0. But it should also be continuous at x is equal to L. So I have this equation plus these conditions. Without those conditions, the equation doesn't have much meaning. The wave function should be continuous and defined everywhere. Outside it is 0. That is defined. It is also defined. So what? No problem. I mean, if you like, you can just do this as a very smooth but steep increasing function. It will still be the same. Now, although I wrote it as k squared, I don't yet know whether E is positive or negative. It should come out of my equations if that equation is enough to describe nature. I shouldn't be obliged to make any assumptions. So at this point, I don't know whether E is positive or negative. K can just be an imaginary number. That is what we will say. You see, I have the equation plus the boundary conditions. Those both should be satisfied. Now we will see for which values of k they should be satisfied. Let's say if k is real, if k squared is positive, then I know that psi should be a times, let's say, sine kx plus delta. If k is positive, then that will be my general solution. I don't know what a is. I don't know what delta is. I also don't know what k is. But we will see. So let's try to determine all those constants. Let's use the boundary conditions. Psi at x is equal to 0 is a times sine delta, which should be 0. But you see, I can either have a equal to 0 or sine delta equal to 0. But if a is equal to 0, I don't have a wave function. So a cannot be 0. The only possibility is sine delta should be 0. which tells me that psi should have this form, a times sine kx, for some value of a. Well, just instead of delta, put pi over 2 plus some other constant. That just gives me cosine. You see, sine and cosine, they just differ by delta is equal to pi over 2. So here, delta is equal to 0 is a solution. If I had started with cosine, then it would have told me that delta should be pi over 2 or minus pi over 2. What do you mean by linearly dependent? Here. Well, you see, if you just open that sign, what do you get? Psi is a sine kx cosine delta plus a cosine kx sine delta. Sine delta is just 0. Cosine delta is 1. Well, in fact, cosine delta can also be minus 1. But since I don't know what a is anyway, so that minus sign I can just absorb in a. So this is 0. This is 1. Now the other boundary condition at x is equal to L. This tells me that a times sine k times L should be equal to 0. Again, I have two choices. Either a is 0. Well, if a is 0, I don't have any solution. I'm looking for a non-zero solution. Then sine kl should be 0. But this tells me that I have a solution not for any value of k. I have a solution only for special values of k. K times L should be an integer multiple of pi. Otherwise, sine kl cannot be 0, and I'm forced to have a is equal to 0, so there's no wave function. So my wave function just turns out to be inside the well is a sine n pi over L times x between 0 and L. If you like, you can just put the equality signs in any one of those. And the energy is, remember, we had defined it as h bar squared k squared over 2m. It's now h bar squared pi squared over 2ml squared and squared. You see, if you try to squeeze an electron inside the nuclei, you are essentially reducing L. If you reduce L, energy increases. So if you just choose an L that is of the order of size of the nucleus, then the corresponding energy turns out to be of the order of tens of mega electron volts. We already know the size of the nucleus from the Rutherford scattering. Now let's see what is A. Let's also calculate the A. Now, A is determined by this condition. From minus infinity to infinity, this is 1. Well, I don't need to integrate from minus infinity to infinity, because you see from minus infinity to 0, psi of x dx, and from L to infinity, psi of x squared dx, and then I have from 0 to L, psi of x squared dx. Well, the first two integrals are, the wave function is 0. So these two terms are 0 anyway. So 1 should be equal to the integral from 0 to L. Now my wave function squared is a squared times sine squared n pi over L times x dx. A squared is just a constant. Well, I will skip the algebra. The remaining term, remaining integral is just L over 2. Or A squared is equal to 2 over L. If you remember last hour when we were discussing the corresponding principle for very large quantum numbers for particle in a box, I said that we didn't calculate it, but it will turn out to be 2 over L. So in the corresponding, in the classical limit, in the large N limit, the measurable probability distribution will be just the classical probability distribution, 1 over L. Now this, of course, gives me only the absolute value of A. It doesn't give me the value of A. Because A can be a real number, a positive number, negative number, a complex number. The only thing it tells me, this equation, is that A should be equal to square root of 2 over L e to power I. Let me put alpha. Whatever alpha is. The A should have this value still with an unknown alpha. But we will see that that value of alpha does not change our predictions. Will not change the results. So we choose, quite often, choose alpha to be 0. Now we have our full wave function. Now here, instead of E, I will just put the N. So for each N, I have a different wave function, and they all correspond to different energies. Energy of this wave function is h bar squared over 2m times n pi over L squared. Now what this tells me is that if I put some particle inside this box, and then if I go and measure the energy of the particle, I can only determine one of these values. Well, if you just prepare your system specially, then you can determine which value of energy will be more probable than which other one. But at the end of the day, independent of how you prepare your system, if you measure the energy of this system, it will correspond to some particular value of n here, an integer value of n over there. No. You see, the probability distribution is the absolute value. You see, the probability distribution is A squared times sine squared n pi over L times x. But I already know absolute value of A squared. Well, the wave function, as we will see on Thursday, always comes with wave function multiplied with its complex conjugate. So that alpha just disappears in all the computations. So that's why, I mean, you can choose whichever value you like. The simplest choice is 0. True. If you put a particle in a box, its energy can never be 0. No, it's not the potential energy, it's the kinetic energy. You see, you can also interpret it like this. By putting your particle in a box, you are saying that your delta x is L over 2. The particle is at the center with an uncertainty of either center plus the L over 2 or minus L over 2. So you are saying that your delta x is finite. But that tells you that your delta p is also finite. So there's a finite uncertainty in the probability. But that tells me that its momentum cannot be zero. If the momentum of an object is zero, there's no uncertainty there. If it has a momentum, it has kinetic energy. So that's why a particle in a box cannot be at rest.
I didn't quite understand why it's independent of alpha. Why the analytic is independent of alpha.
Well, you see what we had done. What we had fixed is the absolute value of a squared is 2 over L. Well, eventually, what will I need? I will not really need the wave function itself. I need the probability distribution. Well, what is the probability distribution? Well, the probability distribution is absolute value of a squared, which we determined was just 2 over L. And we are done. Why did I introduce such an alpha? Well, I just wanted to write the wave function explicitly. That's why I introduced the alpha. But since that alpha doesn't change my probability distribution, you can just choose whichever value you like. It will not be important. You see, this alpha is a phase that multiplies all of my wave function, not just part of it. We will have cases where the wave function will be the sum of various wave functions, not just a single one. Then the phase between those will be important. But here I just have a single wave function. Other questions? So see you on Thursday.